Hello, everyone. My name is Malcolm White. I'm a fifth-year PhD student studying at the University of Southern California with Yehuda Ben Zion, and today I'm joining you from Boston, Massachusetts. As you all know, on the 5th of July, 2019, a magnitude 7.1 earthquake ruptured on the eastern Little Lake Fault near the town of Ridgecrest, California. SCEC and the USGS immediately mobilized field teams led by Rufus Ketchings, Mark Goldman, and Jamison Steidel to deploy over 460 seismic sensors to record the aftershock sequence. Hongjin Feng, Yehuda, and I have since been working with that data to derive high-resolution models of seismic velocity structure in the surrounding region, and I'm excited to share some of that work with you today. The data used in this study come from three distinct sources. First are the 59 permanent broadband stations of the Southern California Seismic Network. The locations of these stations are indicated by the inverted orange triangles. Second are the 15 temporary broadband seismometers deployed in the core fault zone to record the aftershock sequence. The locations of these stations are indicated by the green triangles. Finally, a subset of 78 geophones from the SCEC USGS dense deployment form two rectangular arrays. The first array, with nominally 10-kilometer interstation spacing, focuses on the main shock and aftershock sequence. The second, with 5-kilometer interstation spacing, focuses on an isolated swarm of seismicity on the Garlock Fault to the southwest of the first. We use data from all 152 of these stations, both geophone and broadband seismometer data. The first result from this study is a catalog of nearly 95,000 earthquakes. Compare that with the roughly 36,000 earthquakes during the corresponding time period published in the Southern California Seismic Network's catalog. This catalog begins 1 month before the main shock, and we detect and locate events in raw waveform data to derive a catalog that's independent of any a priori observations. We then iteratively update our velocity model and relocate these events using a genetic algorithm to locate the earthquakes. We solve the forward problem of computing travel times by implementing the fast marching method for solving the iconal equation in an open source Python package that works in 2 or 3 dimensions for both spherical and Cartesian coordinates. Here's a demonstration of wavefronts emanating from a point source at half-second intervals and being deformed by velocity heterogeneity. This tool also provides the ray tracing capability needed to formulate the tomography inverse problem. The point here is that we can accurately and efficiently compute travel times and ray paths through arbitrarily complex velocity structure, and this allows us to solve the earthquake location and tomography inverse problems in some really neat ways. We formulate the tomography inverse problem using the method of Poisson-Voronoi projections introduced by Hongjin Feng and his co-authors earlier this year. Since Hongjin already presented his method earlier today, I'm not going to review that content, but I do want to quickly illustrate 2 key changes that we make to the algorithm in this study. The top left panel here shows a uniform distribution of Voronoi cells, and the top right panel shows the corresponding cell density function as a function of depth. The bottom left panel shows a non-uniform distribution of Voronoi cells, and the cells here have been stretched along the horizontal axis. These cells are distributed proportional to the density function in the bottom right, which is derived from the absolute velocity gradient with a Gaussian smoothing filter applied. We distribute cells proportional to this density function because we want to increase the resolution in the shallow crust where velocity gradients are the highest. We stretch cells along the horizontal axis because we want to increase the vertical to horizontal resolution ratio. We then apply this method to our catalog of nearly 95,000 earthquakes, and we get a model like the one on the right. Here I'm showing you the P-wave velocity structure, a horizontal slice at sea level. I've referenced the depth here at 0.85 kilometers because, well, I've referenced it relative to the mean station elevation, which is 850 meters above sea level. The left-hand panel shows the corresponding slice through the Harvard version of the SCEC CVM, and you can see the increased detail in our model. The white dots here represent seismicity within plus or minus 500 meters depth of the plotted slice. Here is the corresponding slice at 1 kilometer below sea level. And here is the corresponding slice at 2 kilometers. Continuing through 3, 4, 6, 8, 12, and 16, we see that we resolve additional detail throughout the range of depths I've just shown you, 0 to 16 kilometers below sea level. But what of these additional details correlate with known Earth structure? In the left-hand panel here, I'm showing you the event station distribution. In the middle panel, I'm showing you surface geology taken from the USGS. And the right-hand panel shows the P-wave velocity structure at sea level. I'd like to walk you through some salient correlations between the surface geology and the shallow P-wave velocity structure. First, we have the granitic southeastern Sierra Nevadas here indicated by this pink geological unit at the western edge of our region. This manifests as a high velocity bullseye and an associated limb that runs roughly to the south, which envelops a set of 3 relatively isolated seismometers in the Sierra Nevadas. Notice the absence of stations in the northwest corner of our study region and the corresponding velocities that are inconsistent with the granitic surface geology. This portion of our model is poorly resolved. Immediately to the east of the Sierra Nevadas is the Quaternary alluvium of the Indian Wells Valley, which manifests as a prominent low velocity zone near the center of our focus region. To the north of the Indian Wells Valley is the Coso volcanic field, indicated by the red triangle here, and the associated Quaternary volcanic flows. Underlying the volcanic flows are the granitic Coso mountains, and to the east of the Indian Wells Valley are the granitic Argus Range. Both the Argus Range and the Coso Mountains manifest as a continuous high velocity region in our model. The alluvium and sandstone of the Panamint Valley and Range at the eastern edge of our study region here manifest as a large, low velocity zone. And the Garlock Fault near the southern edge, running from roughly southwest to northeast, cuts through 2 low velocity zones. The first, at the southeastern end of the eastern Little Lake Fault, where it abuts the Garlock Fault, has surface geology very similar to that in the Panamint Valley and Range, and very similar velocities as well. The second, to the southwest of the first, correlates closely with the alluvium of the Fremont Valley, which is bound to the north by the El Paso Mountains and to the south by the Rand Mountains. Both the El Paso and Rand Mountains appear as high velocity zones. So you can see that the shallow P-wave velocity structure correlates quite well with the surface geology. And I'm omitting the results here for the sake of brevity, but the shallow S-wave velocity structure shows generally similar features. Now I'd like to show you a few vertical cross sections through the model. The top panel here shows a vertical cross section of the P-wave velocity structure running from A to A prime, northwest to southeast along the eastern Little Lake Fault. I've projected all seismicity within plus or minus 10 kilometers of the plane onto the plane and plotted it as white dots. Notice first the low velocity zone associated with the Indian Wells Valley and the Garlock Fault, and the conspicuous gap of seismicity between the northwestern edge of the Indian Wells Valley and the Coso Volcanic Field. Beneath the Coso Volcanic Field is a patch of shallow, apparently northwest dipping seismicity that correlates closely with a high velocity zone. And at the base of the seismogenic zone, we get a very prominent low velocity zone. The magnitude 6.4 earthquake occurred at the upper boundary of this low velocity region. And the velocities near the hypocenter of the magnitude 6.4 are very similar to the velocities near the much shallower magnitude 7.1 hypocenter. Cross-section B to B prime, which runs from southwest to northeast along the southern Little Lake Fault, cuts across the eastern Little Lake Fault at a 90-degree angle. Notice that the low velocity region at the base of the seismogenic zone continues in this direction as well. And we have a strong cross-fault velocity contrast here with the fast block on the northeast. The majority of seismicity in this cross-section occupies a horizontal interval that is bound on either side by relatively elevated P-wave velocities. Shallow S-wave structure generally agrees with the corresponding P-wave structure with low velocity Indian Wells Valley and Garlock Fault. The deeper structure of this model, however, differs significantly from the P-wave structure. Most notably, the absence of the low velocity zone at the base of the seismogenic zone and a low velocity zone beneath the Coso Volcanic Field that is unique to the S-wave model. The absence of the low velocity zone near the base of the seismogenic zone is problematic for interpretation. If we interpret the seismogenic zone, the base of the seismogenic zone, as coinciding with the brittle to ductile transition zone, we would expect low shear strength and thus low shear wave velocity here. So more work is needed to properly understand the deeper portions of the shear wave velocity model at this point. The feature beneath the Coso Volcanic Field, on the other hand, is relatively easily explained by the increased heat flow and potential presence of fluids that accompany the volcanism here. Section B to B prime, we again see a strong cross-fault velocity contrast between 4 and 8 kilometers, and have difficulty interpreting the deeper portions of this. Finally, we derive VP-VS ratios and observe elevated VP-VS ratio above the magnitude 7.1 main shock and beneath the Coso Volcanic Field, where we find that dipping seismicity, and a reduced VP-VS ratio at the base of the seismogenic zone, corresponding to that low velocity region in the P-wave model. In summary, we've derived an independent catalog of nearly 95,000 earthquakes over a 3-month period, starting 1 month before the magnitude 7.1 Ridgecrest earthquake. And this was largely motivated by the rapid response dense deployment of geophones led by SCEC and the USGS. We've then inverted that catalog for 3-dimensional models of seismic velocity structure, namely VP, VS, and VP-VS models, and achieve improved resolution, particularly in the shallow crust. Finally, we have developed an automated procedure for deriving these results from raw waveform data using minimal a priori information. With that, I'll yield the remainder of my time to discussion.